Hello and welcome to my first video in a while actually for the NES, and in this video I will be showing you how to make a game with VBCC 6502 compiler. Well, this video series will be 3 videos, and in this video I will pretty much go over the tools we need and all of the setup for doing so. So before we go any further, let me show you what we will actually be building. So I have actually finished this game. I have a version that we will go through and build together, and I have a version that I have just released on itch.io, which you can go and check out. So the version we will be looking to build over 3 videos is this one here. So there are 8 levels. It is fully playable and it is a full game, so you can actually complete the game. There is an ending as well where you can put some text if you like for the player to say well done. So you see we've got the mothership there in the form of a Koopa. And if you see up here, we have our icon for our player and their lives. Now if you get to level 2, which I will try and quickly do a moment, then you change to Luigi. And there you go. So each level the colours change and the player alternates between Mario and Luigi. The bullets speed up a bit as well. So that's what we have in store. So first off, I'll go over what I'm actually going to be covering. So we will go over all the tools and bits and pieces we will need for the project. This is just software, so for example, if you've seen the previous video using VBCC, which I recommend that you do, then you will see the NES to tile graphics converter that I use, which obviously you can download from my SourceForge page. So I recommend using that for converting the graphics. And you will also need my NES SoundMaker tool as well, so we can design the sound effects. Obviously the ones that I sort of present in this project, there's no reason for you to keep those. And obviously if you know how to create your own, then you can have fun doing that as well. And I'll also, well, I'll go over the tools in a moment. And then what I'll do is I will start a blank project, and then I will copy and paste functions from the completed game into the new project, and I will then explain what's actually going on, why we need them, and then I'll do some little demos as well to show off what they actually can do. For example, the Sprite Manger for this project, it obviously will handle the player characters, which are 16 by 16 pixel images, and the mothership is 16 by 32. So we will be using 8 by 16 pixel sprites. So we will need the Sprite Manager to arrange the tiles in the correct order, depending on whether we flip them left and right, and then also in the graphics animation for them as well. In fact, I'll see if I can. So where is it? No, it's missing a frame. So if I open up the sprite sheet, although we have this frame twice, you'll see we have one here of him straight up, and then another where he's rotated on his side. And this image here, I have set the grid to 8 by 16 pixels, and I've obviously had it start at 1 pixel wise, so we can have the top row for our color palettes here. So as you can see here, we have one frame of him dying here, and then another of him dying there, where he's kind of rotated 90 degrees. So we can, using the Sprite Manager, we will be able to correctly organize the sprite tiles here. So when we wish to draw him upside down, we can use the sprite attribute to flip the graphics vertically, and then when we want to show him rotated facing to the left, then we can use the sprite attribute to mirror the tiles horizontally, and also have it so that when we tell the Sprite Manager to do that, it will also rearrange the tiles, as we would need to swap them over as well as mirror them. So that's something there. And then also, if you look at the Cooper here, you'll see that it's made of 4 sprites here. So there's a function which handles arranging the large sprites here as well, and it also will manage the mirroring of the graphics as well. So if you flip it vertically, the Sprite Manager will swap the tiles around into the correct order for us. I'll go over that when we get there. And then you see here there's various iterations of the graphics here, which I will go over in a bit as well, as I will create some custom graphics in a moment for us to use in our first project. So like I said, I'll drop in some key functions and some modules as well, so we'll have basically everything we will need for this game, and possibly a number of others as well, which you might want to use the sort of project to build off of. So let's go over the tools we will need. So I'm going to be using a Libre Sprite, which is the graphics editor that I use here. So if I open up our Gumbas here, this is a very versatile graphics editor, and it's open source and free as well. So I highly recommend using this. I will be using that for all of my graphics. And then the NES to tile tool. If you've seen my other NES videos, you'll see me using that. So as an example here, if we let's see, what can we do here? What can we do? Okay, let's give him a top hat, just because. As an example. So another thing to note here as well is obviously so there we go, we've got our Gumba with a top hat there. So one thing to be aware of as well is the color palette is needed for our NES to tile tool. So what we need to do is side by side where your graphics is. So here we go, here's our Gumba here. So one thing to note, the Gumbas in the Invaders game are actually using background tiles, because there's no way we can have more than 8 sprites on a horizontal row without them disappearing. So we are using background tiles for this. So as a result, put these as 8 by 8 here, and then you can either export them as an assembly listing or a binary file. I will choose an assembly file here. And then that tells you how many tiles you've just saved there. As long as you've got your color palette at the top there and your images are made of just those colors, the images obviously need to be divisible by 8, or sorry, your image should be based in tiles, so it should be kind of width-wise, it should always be divisible by 8. And then the height of it should obviously be divisible by 8, but obviously you also need to have an extra line for your color palette at the top as well. And then if you navigate to where that was and open that in a text editor, you'll see we have some formatted tile data for us, where we can just copy and paste that into wherever is needed. I'll give a link to the ROM tool as well. I'll show that in action in a moment as well. So that was how to use the NES to tile tool, which we'll be using to convert graphics. And then the NES SoundMaker tool. I have 2 versions. The one that's already on the SourceForge is pretty much exactly the same as the version I will sort of be using here. So let me see if I just navigate to that a moment. So the version you can use on the SourceForge will look very similar to this. The version up there is using the GBDK version. The only reason why I've switched to using VBCC myself is because it means I can actually run these programs on my real NES. So let's make a quick sound effect here. So turn on the volume controls there. We'll turn on the continuous, and then let's make a interesting sound with sweeps. So that's why we will be needing this tool as well. So you design, you kind of design your own sort of sounds using an NES SoundMaker tool on the actual NES. That's the way it goes. That way you kind of run it in the emulator. You have a good idea of how it's going to sound. Obviously, depending on which region you're running this on, the sounds will obviously alter for you, because obviously they run at different speeds. So that's the NES SoundMaker tool. I will link all of the links for these tools will be at the bottom of the video. Anyway, so there we go. We've gone over the key tools there. Another useful tool is the NES ROM tool. So if you had downloaded my previous project where I showed off using VBCC 6502, I was using the compiler flag 03. So if I, where was it? So this was the project. Don't think it was this one here. Anyway, most of the other make files I was using before was compiling with 03. I've now found that you should not be using that. You should be using 02. And the reason to use 02 is because 03 pretty much, it unrolls all of the assembly language loops and optimizes for speed, not size. And loads of, you'll see that there's a number of different projects here which I sort of started intending to actually go through like a game series at previous times, and most of the time they run out of memory. And the reason for them running out of memory, I think this one uses, yeah, this one's using 03 as well. So this will bring me on now to using, first I'll show you where to get the ROM tool from, then I'll show you it in action. As the as you see here, the actual ROM itself only has 41K for us to actually use. It's using the standard NROM, which has two 16K program ROMs, and it has 8K for character graphics. And I was unaware that the compile flag with free was actually taking up so much memory. And it wasn't until I decided to try and find out how I could actually see what was going on in the ROM itself, to see how much free space I actually had available. So the site I got the tool from is romhacking.net, and it's this one here by Shiru. So when you download it, what you will get will be a zip file, and then when you extract that zip file, you'll be presented with an exe file. Obviously this is fine if you're on Windows. However, if you're on Linux, the way to do it is to have Wine installed, and then if you open that with Wine, so here we go. This is what you can see on Windows as well. So all you do is navigate to the ROM you wish to check on. So first off, I'll show you version 1 of this, and then what you'll see here, this is it shows you the ROMs here. So that's program ROM 0 and program ROM 1. As you can see, we've virtually maxed out all of the ROM here, so there's virtually nothing that can go in that version of Goomba Invaders. And then here you can see the character ROM, which is where our graphics are stored, and then this gives you an outline of where's free. So you can see we've got a fair space free in the character ROM there. So we could have put more graphics in there if needed. So now what we'll do is I'll show you version 2. So version 2 has a lot more in because it's a finished game now. The version 1 was not finished. I was despairing because I'd run out of ROM again. However, I then looked at some of my older sort of programs, and then I also looked at some of the build flags in the VBCC examples folder. So if I open this up a moment here, so as I said, I'm on release 5, and then the samples, if you have a look for the NES here, and then if you look in the build file here, open those with like Notepad, and then if you look down for the NES here, you'll see most of these are all built using free. However, the one you should be using is 02 for your own projects, as I've shown here. So version 1 version 1 has the 03 set there, and then version 2 uses 02. So always stick using this one, otherwise you'll be using double the amount of ROM and you'll run out. So don't do it. That's the main sort of takeaway here. And then another thing which is useful to bear in mind as well. So this is a very useful tool that I recommend for developing on the NES, just so you can see how your project is progressing and whether you are going to be able to complete it or not. So yeah, the NES ROM tool, definitely recommended. And then the last two things here. So I have a reference image that I always use here. which is this one here. So these are a rough NES color palette. These colors here are taken from the FCEUX colors that they use for the emulator. This will give you a rough idea of what's going to be output when you choose these colors, because the NES colors obviously are not RGB colors like modern machines. They will look very different on CRT TVs and digital TVs. In fact, this one isn't the main one. The main one is this one here. And the reason why is because it has the RGB colors here. So when you look at here, you can kind of work out the sort of like the darkness, what that color will be with its red, green and blue intensities here. So you can kind of see how much red is in each of these colors, as well as the green and blue value. So this is useful for choosing the colors for your tiles and various other graphics. So I will include this image with the project today, so you can use it going forward to help you decide what colors to choose yourself. And then also make sure you're happy with VBCC. If not, then watch the previous video of mine. So that is it for the slides here. Let's jump in and actually start some coding. So first off, I will start a new code blocks project. So I'll go for an empty project here. For yourself, just open up the project that I'll supply with you and just use what you need from it. So I will navigate to the VBCC projects, and then I will create a new folder. And then I will select the VBCC compiler. This is why you kind of will need to have seen the previous video, or watch one of my other ones which will show you how to set up the compiler. And then I will just create a main.c file here just for us to start. And we will be using the LazyNes library to assist us with building. And then one of the other things I recommend as well, if you start a new project, is to take a make file from a project that you already know works fine and just copy it across. What I should have had is a template stored. So we'll copy this one across and drop that in. And then I will start now basically dragging and dropping bits from here, which is useful, and then I'll explain them as I go, what it does and why we need it. Oh yeah, I'm also going to need the default ASM file here as well. In fact, so we will need the assembly file there as well. Let's bung it all in there, we want to see everything. So I will call that GI vid1. Make sure that's on O2 and we are using NROM. And then we obviously want to make sure that we are set up for a makefile project here. And then in the assembly file here, the reason why this exists is this is an easy way to get our graphics loaded in here. So the section called chars, what that basically says is the data below is for the character ROM. So we need the assembly file here just so we can tell VBCC in what order to put our graphics. So because I will be using 8x16 sprites, I want the sprite graphics to be using the first character ROM of so there is only one character ROM, but the first 4K, which will take up the first 256 tiles, I want to be the sprites. And then we can leave all of this other stuff in here actually. The sprites themselves, they are using a binary file. So if I come back to the graphics here, and then we go to my Gumbo invaders here. So you see the tiles are literally split up into segments here. So this is the first part of our min font, which is here. I've converted the first 64 tiles here, which are here, and then on top of those I also have a double height character set here as well. So these are dumped above, which I've labelled here. So this is where the double height font set starts, and that's 128 tiles. So one thing to note with this is that if you want to put any of your custom graphics in here, so let's think, what can I put in here? Let me think. We'll put a custom graphic in there. Just think of something. Oh, here we go. This will do. So let's put a random star in there. In fact, let's put both frames in. So we need to make sure we're using the same colours here. Yep, all looks good. So we'll call this version 2. All of the graphics we use, I use in this today. I'll put the raw PNG files so you can tinker around with those. So what we'll do now is we will get rid of this second double height character set here. So let's build. In fact, what we'll do is we have our top hat gumbers here. So let's erase these gumbers and put our top hat gumbers in here. So we don't need that. Let's go back to build some more. So as you noted, the double height characters are 8 by 16. So we need to make sure we say 8 by 16 so that the graphics converter here will arrange the tiles correctly for us. Did that crash? I think it did. Let's try that again. So that's done there. So although it says 64 tiles, that's obviously 64 tiles at 8 by 16, which is obviously 128. So that's all of those in there. What's going on there? Okay, let's try that again. That's better. So we also need an assembly, or rather a bin file here for our sprites. So the reason the sprite files here, they've been padded out to make sure that they're going to be 256 tiles. So this is not formatted correctly here. There we go. So we'll get rid of these. So let's think, what can we put in here? So again, we don't really need these numbers here, as I didn't use those either. We'll stick with this. So as they are sprites, make sure you set the size 8 to 16. And then save that as a binary file. So one thing to note here as well is that none of the palettes are saved at all. Which is why you kind of need to have the palette one here handy, as I'll show you in a moment. So all this does here is this will v-sync. How have I named as? Because it's the lowercase name. Make sure you name this correctly here. There's no one. Sprite Bank G, there we go. There we go. So here's our ROM currently. So if I open that with FCEUX, you'll see there's nothing there. And then if we have a look at the PPU, it's because I've not uploaded anything. Okay. Well, at least it built anyway. So now let's start dropping stuff into it and get something interesting happening. So I will side by side here, and then we will start building stuff up. So I will add a main.h. And then I'll cheat and use a C++ class for our other stuff. You'll see that make sure you format it so that it's using a H and a .c here, and make sure that these things will be in the same folder as well. And obviously make sure you get rid of the C++ stuff. So now what we've got is we've got a utils for utilities class here, or rather a header and module. And then what we also need is what I'm calling the draw list. I'll explain what this is now. So in the other VBCC, video, I called this the draw queue. So VBCC has two different sort of queues that it uses. One for immediately drawing stuff while the NES's display is off, and another which kind of queues things up while the display is on. So when you call or tell the NES to VSync during a vertical blank, then the other list is then emptied and sent to the PPU to draw whatever you tell it to. So the draw list code, what this does is it will handle a queue of stuff to draw when the NES enters VSync. So we can kind of almost forget that it's happening. So we will side by side these a moment here. So first off, we will create these defines here. So we have an S8, a U8, S16 and a U16 to replace signed char, unsigned char, signed short and unsigned short. Make things nice and quick. And then we will have a true and a false value here for defines. These represent the size of a tile map. So there are obviously 32 tiles across by 30 tiles down on the typical NES display. And then here we have some useful defines for putting bytes or words. When I say byte, I mean an 8-bit number, and when I say word, I mean a 16-bit number. And then what we will also have here as well is some bit patterns here for when we define attribute bits. If you remember from my last video, we obviously have the name tables, which are 32 tiles across by 30 tiles down. Each tile is 8 by 8 pixels in size. Unfortunately, the NES decided that they weren't going to have the same granularity, if you like, so they didn't have 8 by 8 tile regions for the color memory for setting which color palettes are used. The minimum size you can set is a 16 by 16 pixel region. However, to compact things even further, 1 byte in the attribute table actually represents a 32 pixel block. So to set colors, you have to play around with bits to achieve that. I think I explained it in the previous video, but just in case, what I'll do is I will explain it in more detail here. So the way that the attribute table works, in fact that's a bad colour for explaining that. Let's try and find something a bit better. Okay, so if you think of each of, in fact, this is still very poor. Okay, that shows up a bit better. So here we have an 8x8 grid here. Each of these squares you can think of as 1 byte in the, as in each of these grid squares here. So there's 8 across by 8 down. You can think of those as 1 byte in the attribute table. However, the 1 byte represents, if I zoom in here, you'll see that there's 4 sub squares per byte, and this represents the sub blocks within that attribute table block. Each of these sub blocks is a 16 by 16 pixel area. So if you wanted to set the bottom left, say wanted to use this palette here, then you would have to set the lower 3 bits of this byte. Just make sure that I'm explaining this correctly here. No, I'm not. So the let's just double check a minute here. All of these bit shifts here represent everything. Okay, so the top left here, that uses the first 2 bits. The top right uses the next 2 bits. The top left uses the next 2 bits. Let's show you what I'm talking about here. So if I show you the bits in a byte here, so top left uses those 2, top right uses those 2, bottom left uses those 2 bits, and the bottom right uses bits 6 and 7. So you can think of it as like a square region like this. This is what's happening here. So this macro here will sort out a byte for you as long as you plug in which palettes into the 4 options here. It can get a bit confusing, the attribute table to begin with. However, once you get an idea of how it works, it's kind of ingenious, really. The compression format for doing this to save the limited amount of memory which is available. So let's get back to copying stuff in there. So we've got the attribute stuff here. We'll also copy in a quick name table macro here, which allows us to poke tiles at a certain location. So what this will do is you set what location you want, and then it will return a 16-bit number of the name table address. And then there's a few more useful ones here as well. So we'll get rid of this one here because we're not using the second attribute table here. And this is the same thing here, but for the attribute table. So the as I'm sure you'll be aware, the NES has 4 name tables and 4 attribute tables. We'll only be using one today and for this project, to keep it simple. And then these are just some bit flags here for working with the PPU control register. And then I have a define here for a array of bytes, which will be setting up for allowing us to draw text, which is obviously very useful. And then the text here as well. There's also a number buffer as well. So I have a custom function for drawing numbers, or rather a 16-bit number. However, one of the cheats that I usually do when I sort of like draw the score or whatever is I drop off the lower and upper bytes, if you like, of the number, so we can have like an extra 0. I'll show you it in practice in a moment, it'll make sense. And then I will drop in some useful structures here. So this union here, this allows us to basically set up a word using the 6502's high byte, low byte format. When you're poking 16-bit numbers into the 6502, you need the bytes to be in the correct order. This does that automatically for us. And then we have a structure here for a rectangle. This will be useful for working out rectangle collisions, which are obviously something which we will need in our game. So I will drop in a whole load of stuff now, and I will explain them quickly here. So we have a print buffer here. Primarily it's for holding on to strings that we need to draw to the screen. You can pretty much use it as a freelance memory buffer. Lots of times with the NES you kind of want to create RAM which you can reuse, as the amount of RAM that the system has which we can use is limited. So although we have 2K of RAM on the NES, in effect we only have about 1K for our actual program to use. So we only really have about 1K for ourselves. The reason why I say that is because lots of the other regions of RAM are used by not only the VBCC compiler itself to work, but also the stack on the 6502. There's also an area where the OAM buffer needs to live as well for drawing the sprites. So these are all things to factor in. This brings me on to another thing I recommend doing as well with your projects, and that's to create what I call a RAM calculator. So the way this works is when you define variables later on, make a note of how many bytes they take, and then at the end add them all up. So for example, at this stage, when I did this one here, we used 299 bytes, out of about 1,000. I say about 1,000, 1,024. It's something around there. I haven't pushed it to find the exact value. I suspect it would probably vary depending on your project. But if you say, or create like a rule that you've got about 1,000 bytes that you can use for your project, then you're probably going to be fine. If you need to add maybe a couple extra at the end, something to bear in mind, which is why I create a load of sort of global variables. So some more I will actually create here will be for the rectangle collisions. And the reason why I can create these now is because I obviously know how much memory the whole project will sort of eat at the end, so I can be more generous now. So lots of times we want to, or we will have variables which we need to kind of reuse over and over again. When we normally in C, when you have a function, you probably won't think about how many parameters you pass to that function. If you're coding on the desktop anyway, it's something that you don't even bother to think about the implications of that. However, when you are passing parameters on the 6502, you're obviously running on an old 8-bit CPU here, which is only running in Hertz. So when you pass parameters, they need to get put on the stack, and all of this is a slow process. So the fastest way is to pass global variables to and from functions. Also, throughout loads of the program's life as well, there will be times where you just want a variable to be a loop holder or an iterator in a loop. So you can think of these as like general purpose variables. We have some 8-bit ones here and two 16-bit ones here, and then should we need one of the special union types here, there's also one set aside here as well. And then there's also some pointers. So one thing to be aware, obviously a pointer on the 6502 is actually a 16-bit number. All pointers are actually 16-bit numbers on the 6502 because the address range is obviously a 16-bit. So these pointers here will be general purpose, again, for carrying out various tasks. So now let's get on to some of the functions themselves. Another thing as well, like I said, I have some functions for drawing double height font characters. So we can reuse a print function. I've created this boolean here, so if you set this to true, then when you print, you'll be printing double height characters. And then when you set it to false, it will be using the 8x8 characters. And then another useful function here as well. This is kind of just a boolean, really. This lets us know. In fact, I'll put that to bool as well, actually. sometimes we need to know whether the display is actually on or off. This is what this will be doing for us here. This here is a global variable for which it will become more apparent later on in the project. It's so that we can let the other sort of actor managers know what the current level of the game is. And then this variable here, this is for us to generate random numbers based off of just continually ticking on as the project runs. Every now and again, if we want a random number, we'll just interrogate what tick this is actually on, and then use an AND mask to get the bits that we need for like a random number. So what we also have here is we have two error trap functions, one which just takes a string and the other where you can pass a number and a string. So when I debug all my programs, I always have an error trap and an error trap with a number. And the reason for that is lots of times throughout the whichever project you're on, you need to check that the parameters for something is what you expect them to be, if they can change. And if you find they are out of range, then you need to throw an error and alert yourself that the error exists. And obviously the way to do that is to tell the NES to tell you by drawing a string to the screen and freezing the flow of the program. Likewise, the error trap number function here, sometimes a string name is not enough. Sometimes you need to know the value that is that has occurred, which shouldn't occur, and that's what that function there is for. So let's carry on. Now this function here, this will turn on the display, and this one here basically wraps the relevant LazyNes function here. So this one here will turn the display off, and then this one here will basically turn the display on using the respective LazyNes function there. And then this brings us on to another useful one we need here, as we are using 8x16 sprites, and we want the we also need to set the background characters to use the second bank. That's what this does here. So the LazyNes library, it has some shadow registers, if you like, which will get copied into the real NES registers when we call vsync. Which is kind of what's happening here. These will set the PPU control register to turn on large sprites, and also to switch the default tile banking area for us, so that sprites are first and the background tiles are second in the PPU video RAM. So I will drop in some more useful ones here. So this function here will do as it says on the tin. It will set only the background color for us. And then this other function here, this allows us to upload a color palette to the PPU. This should be just used for the background tiles. Now what this function here does is it allows us to update one color palette in the palette buffer here. So where is it? Okay, it's obviously going to be in the module file here. So what I've set up here is there is a RAM buffer of 3 bytes, which is called the palette buffer. And basically you can alter those 3 bytes whenever you want. And then when you call the palette buffer upload, you specify which palette ID, and then it will basically upload those 3 bytes into that that palette in memory. So you can basically manipulate the palette whenever you want, or just one color of it, which is how I got the effect. Wait, if I get to this one here, I'll show you this again. That's what's going on here. The color cycling here is achieved by updating the palette. So if we look in the PPU here, you'll see that that color there is basically cycling through the whole color row here. It's literally going from 2 0 there and then working its way across. You can always find use for palette shifting. So let's get back in here. Oh, there's a duplicate function here, which I was not aware of. Well, that'll be corrected now. So here's our standard print function here. If you've used BASIC or you've done any of my previous videos, then you'll be familiar with these. And that wouldn't be complete without center print for handling print and text centered on the screen. And then what we'll also need now is we need the relevant tile functions to go with that. So this function here will draw a 16 by 16 pixel block, although it's not really. In fact, oh yeah, it is needed actually. The let's get in here. I think the min font. Yeah, here we go. This character here is actually the floor tile. Is that right? Or it might be this here actually. Yeah, I think that's right there. That's it there. So to print out a 16 by 16 block, you need your tiles to be organized like that. So you need the top left, top right, then bottom left, bottom right. Organized in a row like that. And then there's the standard tile put there and tile put double height, which will obviously be useful for our double height font set. So let's get back to copying some more stuff in. Okay, we're done with this pretty much now, which is good. So we have tile put big. This isn't actually used in the game, but I'll leave it in for you anyway. Basically, this can draw like a large chunk, if you like, whatever size you want it to. And then we have some tile fill strip functions here for basically spamming a tile either horizontally in a row or vertically in a column. Here's our function to draw a 16-bit number. So one thing to note here as well is some of these functions, they use the global variables here. So you will need to get to grips with making sure that you don't have anything stored in these that you need prior to calling these functions. Otherwise, the values will get overwritten inside these functions, and then when you go to use them again, they will not do what you expected them to do. So print number is straightforward here. Now this one here, what this will do is it will take a byte and then it will place that byte into the attribute RAM attribute table, and the parameters you pass in here will be in blocks of 32. So you have to envision the attribute table as I said previously, and then to create a byte, use the attribute tile color defined here. I'll show this in action in a moment, just so we're clear what's going on here. And then what I'll do here is the rectangle overlaps function here. I will update this to use the newly created rectangle only variables. Previously it used all of the other general purpose variables, whereas now, because I know we've got the space, we will change that. And then obviously this one here clears the screen as well. One thing to note when you're going to clear the screen, make sure you turn the display off. There's a limit of how many tiles you can actually draw in one go while the screen is on. Like I said, the VBCC has like a buffer somewhere. Sorry, not VBCC. LazyNes has like a buffer somewhere in RAM, you need to sort of say, or rather you have to sort of create your own sort of buffer, and you have to decide how much memory that will actually have. I'll get into that in a moment. As all these tile drawing functions and the print functions, they will check to see whether the NES is display on variable is true or false. If it's false, they won't use the draw list functions. They'll just use the immediate ln functions that LazyNes has. So, for example, the lists which LazyNes has, they have ln push and ln list. So ln push is the one that you use if the display is off, and ln list is the one you use if the display is on. I think I've got that right. And then in here there's some options already sort of set up for you here. So you'll see the way these work. ln push here, this expects an unsigned 16-bit number first, which would be the destination address. You then say how many bytes you're pushing, and then you pass a pointer to the data. And then that's kind of the same with the list here, except the list, it has an address where you're going to send the data, and then it has a pointer. And then one thing you also need to do is to set up a direction flag, which gets added to the high byte of the address value you pass in here. And the reason why you pass in these data direction flags here is to say whether the tiles you're passing should go across horizontally, or whether you want them to be drawn vertically going down or up the screen. If it's horizontally, then the value just needs to be updated by 1 to draw across the name table. If you're drawing vertically, then obviously it needs to add 32 to go to the next vertical line. Just some info for you there, so you have an understanding of what's going on. And then I'll copy all of these in here. So this is the draw list size here. It basically uses an array of bytes set out in the module, source module here, which I will copy in now as well. And like I said, this handles the draw list for us automatically in the background here. I've already worked out how many bytes of RAM this uses, so it's fine. So you'll see here, if you try and chuck too much into this list, it will throw errors for you, kind of give you some info. You might want to expand the names to be a bit more meaning to yourself. Trial and error will get you to grips with this properly. So one thing to note in here as well is the print function from in here is kind of either backed by the utils print here, or it outsources it to the draw list here, where it does everything in the background. Basically all it does is it adds all of these bytes into this draw list here. So it's kind of like a list of jobs to actually do. And then when the PPU enters VSync, LazyNes sends this list of stuff to draw to an internal function which does all that for us. So what I'll do now is I will get the utils stuff in here, and then we'll get some stuff drawn on the screen so I can actually start showing stuff off rather than just wittering on. So what we have here is let's copy these ones in here. So as a side note here, if you're not using the rectangle collision functions at a specific time in your project, then you can obviously reuse these variables for something else. This is the main reason for having all of these exposed here, is so that you can think of them as like global variables. Right, I'll be back in a minute. I'm just going to make myself another coffee. So let's quickly side by side some of this a moment here. So there's the error trap prototype here. And then what this is doing here is we are changing the background color to black here first. Right, I best set that up here. So some of these defines here are expected to be found in the graphics define header here, which is another thing I generally always implement as well. This just keeps track of where the graphics tiles are. I'll drop all these in here. As they pretty much will exist. So you'll see here, these are this is the start of our standard character set here, which tile starts the ASCII character where the font set starts from. Usually always start from 32 because that's the default sort of space character, just an empty character really. And then we have the important thing is how many tiles it's using. And you'll see we've done the same for our double height one there. This is where the floor tile is. These are the sprites where they live. And this is our Gumba, which for us, and this one will be the top hat Gumba. And then one of the things we've not defined yet is the color palettes. So we'll add in a file now for our color palettes. And this will reference these here. So one of the other things I sort of have with this project as well is I also have, if I open up the default one here, oh no, I don't have it in here, it must be in the level manager one. Okay, it doesn't really matter. So this is where the color palette image comes in useful here. So you kind of need to have this one, and then you'll need to have your tiles in front of you, and then you need to pick these three colors here which will align to these ones here. So for this example, let's go for the first palette. Let's go for 5, so we're going for that color there. We'll go for 15. Bear in mind these are in hexadecimal here. And then we will also go for 30 here. And then don't worry too much about this for the sprites. Okay, let's have a look at these a moment. So the colors here, they're just kind of like a reference, if you like, or a starting color. These won't actually be used in the actual game unless you kind of want them to. But it will be up to you to pick a color from these palettes here. So when I choose these colors here for default, they are kind of going off of the so if we open these colors up here, these are rounded to the nearest 8, as that is kind of the color that the Game Boy uses. And the reason why I don't use these colors specifically here is because it would lock the graphics converter to those colors in FCEUX emulator. So just keep all the colors aligned to the nearest 8 in your actual images. And it's only like a reference color anyway, just to represent the 3 colors that you will use. And then when you come to actually create your palettes, make sure you have like an image like this in front of you so you can decide what colors you really want. So we want our sort of Mario color here for the first. So we'll have him as 06 for the dark. In fact, no, let's go for 07 actually, I think is what I chose. And then the red we'll go for 16, and the pink color we will go for, let's try 36. There we go, that gives us our default palette to start with. We can obviously choose different colors for the Goomba and the Koopas here later on. So that's our palettes defined there. And then you'll see in here the error trap obviously needs to print out our characters. And it's turning the display off, and it's using the ln push function there, and then turning the display back on, and then an endless loop where it calls NES VSync there. So the utils function here also uses the draw list functions. Like I said previously, it does all this for us as long as you call these. So when you finish up everything, when you call NES VSync in the background, it will handle drawing the draw list for us automatically. This is the actual LazyNes VSync function here. And then it also will clear the draw list for us. And then it sets the boolean to say the display is on. I don't think there's anything too magical going on here really. Everything is using the LazyNes stuff in the background here. So if you need to sort of get a good understanding of what's going on, then obviously go through and inspect loads of this a lot more. So another thing to note here is the palette buffer, like I said, that lives in here with 3 bytes. I'll show that off in a moment. This might need some detail in here. So I've got like a tick timer thing in here, but it's only using 1 byte. And the way it works is it uses 7 bits for the actual timer, and the upper bit, bit 7, is the value to say whether it's true or false, as in whether the countdown has occurred with the timer. If it has, then it will return true. So so you'll see in here as well it uses GA. We'll stop that here. We use a temporary variable in here. There we go. So look at some of these do use the global variables here in these functions. The ones which usually get used are the 16-bit ones, because they're used to basically hold an address in memory where we need to send stuff to the PPU for it to draw some tiles or something for us. So let's go down to the rectangle collision one here. As we you'll see here, I did have some other rectangle functions here where you actually passed a pointer in, but I decided to remove those as this would be quicker here. We always need to think about speed with the NES. So the reason we are using some temporary variables in here is so that we don't destroy the current contents of the rect variables here. So for example, if we had a load of rectangles which were the same size, the only thing which changed was the coordinates where they are placed on the screen, then we could quickly just update a few, just the R1, X and Y. Maybe they're the only ones that need to change. Then that would give us a speed increase. We'll need to double check that these actually work in a moment as well. In fact, I think that might be what's going on there. Right, let's build this a moment, make sure there's no errors. Okay, there is. Let's quickly get something going on so we can display some stuff. So we don't have those two yet, so we won't do anything there. Let's bung in the input manager so we can actually get some joypad stuff going on. This is all pretty straightforward here. These button flags here are for the joypad bits. It uses these two variables here. We can actually hide these. There's no reason to expose those actually, so we'll do that. So at the start you call the init function for the input manager, and then in the main loop you just call input manager update, and then throughout you just check whether a key is down or whether a key was pressed. So let's open that one up. So there's not a lot happening in here. Let's rename these a moment. So this is another thing I commonly do in my code, is to represent what would be known as a private variable. I'll just put a Z in front of it. So when I'm sort of coding normally, I won't be aware of the variables. And you see here this function here, ln getPad, is the LazyNes function to get the joypad there, and then it just returns all of the returns a byte, and the bits of that byte correspond to the joypad actions here. Let's, oh yeah, we get something up and running quickly now. So we will get busy here. So we want the display off. Turn big sprites to on, and then we will set up our tile palette. I think we only defined one. Yep. So you pass in the palette ID you wish to change, which goes from 0 to 3 for the background tiles. You then pass in how many palettes you want to set, and then the pointer. So that's another thing here. Have we got the graphics defines? Yes, we have. So, and then what we'll also do is we'll set the background color to, let's see, what color should we go for? Let's go for 0B. There we go. Set the background color to B. And then we will clear the draw list first off. Turn the display on, and then we are in the main loop here. So what we will do here, so in between the display being off and on, we can basically draw a load of stuff to the screen. So what we'll do is we will turn on the print double height to true, and we'll print center at tile 20. Now let's address these errors here. So there is let's have a look here. Oh, I'm missing a semicolon somewhere. Oh, wait there, it's saying there's a colon somewhere, but it's expecting a semicolon. It's because I've not defined that, I think. Let's go up there. NES display off. It's because it's not including main.h. Here we go. Happy days. So that's one thing to be aware of as well. Only include the LazyNes header in certain places. Is it in there? No, it's not. So just in utils is where I'll sort of declare it here. So that's built now. So there we go. We've got our green background there, our white font set there. So we've got our sprites loaded in there in pattern table 0. And here are all of our characters loaded in. These are arranged wrong, I think. In fact, where is that star? That's at tile 44 in hex. So let's make a note of that. And then what we'll also need as well is, or rather are, some more palettes. So that's for our sprites here. Let's bring in the Sprite Manager as well. No, that's the Sound Manager. There we go. So the Sprite Manager here, lots of times you'll want to kind of tailor this to the type of game that you're making to some degree. You'll see here there's only 4 functions here. Some of these you'd probably need to change depending on what your sort of project graphic wise supports. Some of the stuff won't change here, like the sprite attributes here, the palette IDs. So let's load these in here. And then you'll see in here the way to use the sprite functions is we have some global sprite parameters here which you set up before calling the sprite commands. So you set up their X and Y positions there. The sprite graphic ID, that's going to be the starting tile. The sprite attribute, that will be a combination of the color palette bit and potentially the flip sprite attribute bits as well. There's also another one there for background in front of sprite as well. That's something we'll have a look at quickly as well before I sort of wrap this up. I want to make sure that there is at least that you have, before we sort of finish this up, we'll have the Sound Manager in. You'll press a fire button, we'll play a sound effect, and we'll also have a load of sprites moving around as well, and that will be the limits, I think, for this video. It's gone on for quite a while. So I'll quickly talk about what's actually happening here. So you pass in the relevant palette ID for the sprite set palette. Side by side these a moment. And then you pass it like a color palette here, or 4. So let's set up some other colors here. So the we got the background color is B. So let's go for, let's say OC, 1C, and 2C. There we go for our sprites, and then we will chuck in another font set color here. Let's go for 0, 1, and 2 there. So to draw sprites, you set up the attributes here: X position, Y position, graphics ID, attribute, and then depending on the size of your sprite, depends which draw function you would call. So for example, as Mario is 16 by 16, you would call the first one here. So we will do that now. Let's include the Sprite Manager there, and then did I call it? There we go. Let's set up some stuff now. And then the easiest way to get our graphics going is to create an array which contains the starting tile. So if we have a look in here again, and then we set this to Sprite 8x16, and no, we're in 8x16 here. So you see here, that's tile 0, that's tile 1, that's tile 2, that's tile 3. So 4 tiles per sprite. So for him to animate, we need 0, then we need 4 there, then 8, and C. But what you want to do is, if he's stationary, you draw this one, and if he's moving, you alternate between the stationary here and then the walking here. So the stationary is 8 in hex, and then that will give us our, in fact what we can do here, give him a state as well, and then we'll say give him a state there. So we'll say that if the if he's walking, then he will animate. So if he's walking, he will jump into one of these frames here, otherwise he won't. And then he's using palette 0. So let's move him left and right there. Won't bother doing any boundary checks for now. Oh, I've not uploaded a palette for him, so he's okay, we also forgot to do that. There we go. There's our Mario sprite there moving around with the joypad. So let's have it. We'll set the default as that, and then we will move these above. Nope, we want that below there actually. So if he's doing that, we'll change his state to walking. And then if he's walking, in fact we want another one as well, don't we? We want to know what way he's facing. See whether he's facing left or right. That's where these enumerations come in useful there. So by default, I believe he's facing to the right. I'll come back in there in a moment. So if he's walking, then what did we say it was? 16. How many frames? We got 4. What's it called? Frames. So here what we're doing is we are taking the correct tile ID for Mario from our frames list here. If he's walking. And another thing we need to do as well is if he's facing left, then we need to add a flag to the sprite attribute byte here, telling it to flip the X or mirror our sprites. So if we build that again, it should look a bit more interesting now. I must have one of the IDs wrong. The animation's too slow as well. But you can see the thing we're going for here. What number did I get wrong? We've got 0, 4, 8, and C. Ah, there we go. let's speed up his animation as well. That's far too slow. Let's give it a define. Let's go for 8. Still don't seem to be working right, does it? It's got to be due to here. It's probably because... Is it that? Maybe we should just stick with There we go, that seems to be working a bit better. So let's add in some more controls from there. Let's draw some tiles as well. I've got some floor tiles in there now as well. Let's put them below actually. So I'll also demonstrate the attribute now as well. So we will use let's use one of the rectangles there. To hold our attribute byte there. So what we'll do is, now what you do is you set which palette you want for each 16 by 16 pixel block of the 32 by 32 pixel block hole. So if we started at the top left, then in fact what we'll do is we'll use 0, 1 and 2 and 3 there. So we'll use all 4 palettes. So let's make 2 more palettes here. So let's get some colors. Let's get some more colors. Let's go for 0, 2. Go for a load of blues. And then let's go for, let's see, let's go for the browns and yellows there. In fact, no, because that's Mario's color. So let's go for some greens instead. There we go, we've got 4 colors now. So we'll draw that on line 20. And then we'll so let's draw a Gumba now. So this is where the tile put big comes in, because the Gumba actually is composed of 6 tiles. So what we need to do is I think where are we? So that's, I think that's 5. So let's try 5. So let's try that. Okay, so you can see some of the colors change there. And there's our first top hat Gumba there. So if we have a look in here a moment. Oh, it's not. Oh, we haven't uploaded the other palettes. I didn't tell it to. Okay. So we want to put that to 4. There we go. So it has uploaded those colors, but that's because it's using 2.0 there. It looks very samey, which is obviously the line in the attribute table. So we will let's print above there a minute. Go for line 3. And then let's, so what color? Let's update one of the palettes. So let's see, what should we go for? I think we'll mend the first one. So what you need to do is you need to set it up first. In fact, did I? Yes, it's available for us to change in a moment. And then we'll change palette 0. And then we'll do it every time. What's it called? See, what did we start as? 36. So it'll be, what we'll do is we'll add 16 at a time. So we'll cycle through all of those. Ah, it's because we're not setting it back. Okay, is better check to make sure it's not actually using GA. Okay, what am I doing wrong there then? Don't seem to be working. we're using GA in here. Must be because that colour is not actually being used. Oh no, it doesn't look like it's actually updating it. Maybe we should be changing the first. Ah, in fact, I know what it is. That's out of range, I think. There we go. The pointer was out of range. So before I end the video now, what I'll do is I'll drop in the Sound Manager. So there are a load of sound effects in here already. I'll leave those for you to have a listen to. And by all means have a play around with the Sound Creator program. So the bytes which are spit out here are obviously from the Sound Creator program, and then the Sound Manager has a function there called Play Sound Effect. So to use the Play Sound Effect function, first thing you need to do is you need to initialize the Sound Manager, which we'll do now. And then all that does is we poke a load of numbers to the APU, which is the audio unit in the NES. On one of my videos, I believe I went through and spoke about the various registers here. So you've got 4 sound channels on the NES, I'm sure you're aware. There's 2 sound channels which have sweep functionality in them, 1 and 2. Sound channel 3 is, no, sound channel 4 is the noise channel. I have implemented the triangle channel here. So we will So simple as that. So I think that will do it for this video. This basically has everything you need to get started with a game. We have all of our graphics already loaded in here for our game. Have a play around with the tile commands to draw these out. Add in some more palettes for the sprites. Have a play around animating those. Make sure to have a play around with some sounds as well. And yeah, that's it for this video. Thanks for watching. Let me know if you've got any comments for stuff you want me to maybe drop in the next video. Right, that's it. Catch you later.